In the name of God. My name is Maryam Jamshid Nejad, who want to answer this question. What is SL parameter? SL is shortens of source level. Our purpose is to calculate all parameters that we need in the acoustic tomography knowledge during the calculations. We have formula number 1 and formula number 2 in this page. If you look at this picture, we have two different transducers, or we have a pair of transducers in two different sides of the river. One of them is upper and the other is downer. That transducer 1 or station, upper station, and transducer 2 or downer station. Here we have the horizontal distance between these two transducers or these two stations, that the name is L, and the arrival time from at the upper and downer station we can calculate. With all these, we will have the U, the cross-sectional velocity along the transmission line. The formula number 2 is calculating the stream flow, Q. For calculating the Q, we need to have A, or the area of the Q, a cross-sectional area of the stream along the sound transmission line, and angle. The area will calculate simply, and the angle between the transmission line and the stream axis. The transmission line is the line that we see by the U, and stream axis is showed by V in the picture. The difference between these two axes is theta. Okay, and the number 3, formula number 3, we have RL equal SNR equal SL minus PL. What is SL parameter? Is the source level with the unit decibel related 1 micropascal at 1 meter. We want to know much more about SL. Hydrostatic pressure. The air around us at sea level pressure down by as 14.7 pounds per square inch. We don't feel this pressure because the fluid our body inside body is equal by the pressure is outside of our body at the sea level. But when we goes down in the ocean or seas, for every 33 feet, and that's equal by 10.06 meter, the pressure increases by 14.5 pascal or 1 bar. Hydrostatic pressure is the pressure that is extracted by the fluid at equilibrium at a given point within the fluid. It's because of force of gravity, and the depth will increases at the water level from the surface tile that point in depth. The weight of this water and the denser of fluid above it, it's important, and it will increases the pressure on that point in the depth. And this is the hydrostatic pressure. And how we can calculate this hydrostatic pressure? To calculate the pressure, hydrostatic pressure, we need to first have R, parameter R, G, and H. G is the gravity, the acceleration of gravity, and everybody knows. H is the height of the fluid above the object that you can measure it. And RHO is a density of fluid that depends on the fluid that is in our exam and our test in the project. And we have these three parameters, and we will have solved the pressure. And also, to solving the pressure, same as we see in the up, the pressure, the force, and density, the formula have written here. SPL, sound pressure level. Sound pressure is the most easily measurable quantity. This is the fluctuation of the pressure in the fluid medium like water and air. Microphones measure the vibration in air pressure, ignoring the steady atmospheric pressure, usually for frequencies between 20 Hz to 20 kHz. For various low variation frequencies below than 1 Hz, it's better to use for meteorology. Hydrophones measure the acoustic pressure in water and are insensitive to the hydrostatic pressure, which is usually greater, much greater than any fluctuations that we introduced in the previous slide. Unit is the most important. The pressure unit in SI is Pascal. Pascal and equal by Newton per square meter. The standard reference pressure in air is 20 micropascal. Decibel sound pressure level, or the ratio of measured pressure in this value, expressed in logarithmic terms. We use the logarithmic terms to express this decibel. For human hearing, for linking the by human the pressure that by human hearing, it's watts per a square meter, but this is very useful and good for physical effects, for such as localized heating. But it's hard to measure directly and is usually calculated from the acoustic pressure and knowledge of fluid properties. Intensity. To measure intensity, we need to have three important parameters: P, pressure; rho, fluid density; C, the speed of sound. For air at 1 bar, that's equal by 100 kilopascal pressure. With this pressure, with the temperature 20 centigrade, the fluid density is equal by 1.19 kilogram per cubic meter, and the speed of sound is equal by 344 meter per second. To give, such as you see, rho.c is equal by 409 kilogram per square meter second. Or rails, 409 rails. We can also say it's call it rails. It's the name after Lord Railway. This value rail with environmental conditions. It's for environmental condition, and Mr. Lord Railway find it at about and this environmental condition, this average or duration is between 400 to 420 rates. American Standards Association. A reference level of 1 picowatt per square meter for intensity was set in 1932 by the American Standards Association, and 20 micropascal chosen for the reference pressure in air at the same time. Both are typically for the tonal threshold level of human hearing. and the most sensitive frequency, the band between 1 to 4 kilohertz. Okay, now imagine the acoustic pressure must be 20 micropascal if the intensity be 1 pico watt per square meter, and the impedance be if the impedance be 400 rails. But if our impedance be except of 400 be 1.5 megarails, then our pressure from 20 micropascal will be 1225 micropascal. That's same situation, but different impedance. In 1970, the 1 micropascal pressure reference level was chosen by the US Navy for their underwater work. Other various derived reference levels include the hydrophone receive sensitivity level referred to 1 volt per micropascal for the sensitivity of the hydrophones. However, the original aim of choosing the very small 1 micropascal reference was to ensure that pressure decibel level were always positive. We want to be sure, the scientists wants to be sure that this level that they choose for the standard level always be a positive number. Decibel versus Pascal. Whilst the decibel scales make multiplication and division easier, it complicates addition and subtraction. Where this needs to be done, for example, when there are two or more sources contributing to a sound pressure, it is necessary to first convert the data to the form which is additive. The linear equivalent of a decibel sound pressure level, that's name is SPL, shortened, is the sound pressure or acoustic pressure. So if two SPLs need to be added, they should first be converted to sound pressure in pascals. Correlated and uncorrelated sounds. Correlated sound can be made by a coordinated array of sources, all activated by the same electrical sound signal. All activated by the same electrical signal. The table next page predicts the sound pressure generated at a point by two such sources positioned at that their sounds will be the phase and reinforce each other. As you see here, we talk about two correlated sources and two uncorrelated sources. Box 1 and box 2 both are similar, but upper is about correlated sources and the units for sound pressure is Pascal. But the downer box is about two uncorrelated sources and unit for and unit is square Pascal because it's a mean square pressure, not sound pressure. It's mean square pressure. For this project, the source 1 is constant, but source 2 has changed. The third section is that write two correlated sources or two uncorrelated sources. for sound pressure, we have plus two different sources to each other. For example, for first row, we have 10 plus 10. For second row, we have 10 plus 3.16. For third, also like this, pile n. But for SPL, we don't have same formula for add-up. As you see, 140 plus 140 is 280. But here has been wrote 146, not 280. So its formula for add-up is different, and we have different numbers here. And if you see the difference between two boxes is in end columns for SPL. For first box we have 146, but for second box we have 143, and 3 decibel is different between these two boxes. For each row, 142.4 versus 140.4. About 3 decibel also difference. So we talk about these things here. Sound pressure is the most easily measured quantity and provides the basis for the most commonly encountered decibel level. The audio band sound pressure level in decibel as used in airborne acoustics. Underwater the principles are similar, but the reference levels use a different convention. Here we have an animation that is like this. This animation shows the source that have pulsing the signals, and the signals with the same distance in around the source equal distance and we tape a circle far away, and like this. And as you see here we have a pure tone sinusoidal variation at the signal frequencies that between two peak, the duration time between two peak is t, this period is t, and in vertical axis between two peak is pressure. On this red ball, the pink ball is, and here the situation here, that what the pressure, what happened to it when the source pulsing the signal, and when it's red, the signal's increasing to the peak time, peak point, and when it's blue, the signals have decreased, the pressure decreased. The acoustic pressure. The idealized simple source shown in the previous picture, shown the pulsing sphere radiates sound in all directions and received by the smaller spherical hydrophone. That's a little ball was hydrophone. That its place is constant, and fixed and don't have any moved, and the distance between microphone and source is a fixed distance. Okay. Here it shows the pressure versus time. And the measure of acoustic pressure P at this point, as in shows that when it's red, we have increasing pressure, as you see in the picture. When it's red, we have increasing pressure here to up. And when it's blue, it's decrease pressure. It's comes down. Pressure comes down, as you see here. Yes. And P is here. P is shown by the peak to peak, as I said, and although the RMS, a root mean square value, is often used to give an average over a period. A source level characterizes the properties of the source by measured using a hydrophone at the null distance, as I said.